Okay, it's 11 o'clock. Good morning, Happy New Year, and welcome to year 18 of Chai and Wine. Okay, so as usual, for those who are coming for the first time, Chai and Wine happens on the first Sunday, the third Sunday, and if a month has a fifth Sunday, on the fifth Sunday of the month. First Sunday, we are always here at Prithvi Theatre. Third Sunday at Ruparel College. Fifth Sunday is an online session from a lab in PIFR. Okay, so before I introduce the speaker, just to tell you about the upcoming sessions. The next one, which is 15 days from now at Ruparel College, our mid-month session is called Sitare Zameen Par, which is on very high intensity lasers. And that's going to be, or very short pulse lasers also, that's going to be at Ruparel College. A month from now over here, we will be having an session by an astrophysicist who also does a lot of high performance computing. It's going to be on the current something from the in the year of astrophysics. But let me start with today's session. It's an absolute pleasure to welcome Professor Sabyasachi Mukherjee, who is from the School of Mathematics at TIFR. And he did his his bachelor's in Kolkata. From there, he went to Paris for a master's, to Germany, to Bremen for a PhD. Then he was at Stony Brook for a few years teaching there. And then we were very lucky that he decided to join TIFR. Now, of course, I mean, yes, he has got the Vigyan Shri Yuva Award. He has got the Infosys Prize in Mathematics. You know, he is one of the foremost mathematicians, young mathematicians today in India. And more than that, he likes to talk about mathematics and, try and convey the excitement of why real mathematicians who do mathematics, which is not the same as a school level textbook mathematics, find it so exciting. And in particular, this area called dynamical systems that he works on, he'll be telling us about that. Online audience, if you have questions, please put them in the chat in the YouTube box. We will monitor the chat and take them up. Of course, here you can raise your hand and ask a question. And remember, you guys, online audience, you don't get chai. Here you will get chai, and also we'll have a chance to ask questions after the chai break as well. So on that note, Shubho, all yours. Just remember, there's no mic for these guys. The mic is only there for the online audience. And now you can share your screen.
Okay. Yeah. So thank you for the invitation. Thanks, Arnav, and thanks for the introduction. Let me see, what am I supposed to do? Yeah, good. All right, so yeah, great to be here, to see all of you here. So I want to talk about dynamical systems, but of course I'll go slowly. I'll say what these things are and why people even look at these things. But more importantly, as you see the slide, the first sentence over here is not dynamical system. Dynamical systems come later, at least. Philosophically speaking, I'm not going to teach you what a dynamical system is. I'm not here to tell you how to study dynamics and all. I want to tell you how basic things like solving a polynomial equation, doing something very basic, either that comes from a real life problem or something that you see in school, actually leads to interesting dynamical systems. And I'll tell you what it means. And then I want to talk about experiments. This is something which is probably very different from the kind of math you see in school. You usually just have a formula, you have a triangle, you have some basic objects that you play around with. There is no experimentation in math. Somehow people feel like experiments are they belong to physics, chemistry, biology, and so on. I want to, if you have that.
There's an echo. There's an echo on YouTube. So just your thing off. Not. Yeah. No, your.
How about now? I think it was sharing device audio. Yeah, I just turned it off. Do you still hear echo? Is there any echo? One.
Sometime the lab.
Okay. I will share the screen, but there was this share device audio option, which I just turned off.
Yeah, now it's good.
Now it's good?
Now it's fine.
Great. Okay. All right. So I want to basically show you with examples why it's important to perform experiments even for a mathematician. So but let's at least non-mathematically define a dynamical system. So what is a dynamical system? As the name suggests, a dynamical system is anything that changes over time. And it's a branch of mathematics that did not come from pursuit of pure knowledge like numbers and shapes and so on. It came from physics. As I'll say shortly, the main motivation for studying dynamical systems came from understanding the planetary system, understanding whether the solar system is stable, and so on and so forth. But then there are many other examples of dynamical systems. Just think of anything that is changing over time, any system that is evolving. I don't want to give you a precise definition. Anything that is changing over time. Could be a planetary system, as you see over there. Could be population, which I got this population of fish. Could be weather, could be fluid or gas. What this picture is showing is there's some red smoke coming out of the wings of an aircraft and it's creating a vortex. So anything that is changing over time is a dynamical system, and a mathematician wants to understand long-term behavior of these things. But firstly, even to make sense of studying such things mathematically, I need to somehow model these things mathematically. Otherwise, what am I studying? I can't just look. Then it's just pure experimentation. As a mathematician, I need to somehow model them. I'll not tell you exactly how to model a complicated dynamical system using math, because that amounts to understanding various features of the dynamical system and then write down a differential equation and so on and so forth, at which point you'll find it extremely boring and technical. But let's come back to the motivating question. The motivating question is whether the solar system is stable. This has, of course, been an important question right from the beginning of science. We have the solar system. One could think of a more general question about some number of bodies interacting with each other, but let's just think of the solar system where we have the sun and we have the planets revolving around it, and then we have moons revolving around the sun, around the planets. And the question is whether this whole system is stable or whether there will be a point in time where Jupiter crashes onto Saturn and the moon of moon of Earth crashes onto some moon of, I don't know, Neptune or something like that. And this was actually considered to be an important problem even about 150 years ago. There was a king of Sweden who put a prize money for being able to solve this problem completely, or even if somebody cannot solve this problem completely, even if you make important partial progress towards understanding the stability of solar system, one would get some amount of money. It turned out that this was around the turn of 19th century. It turned out there's a mathematician called Poincaré. I should have written it down. I should. This person is basically the founder of dynamical systems, Henri Poincaré. He claimed that he has a complete solution to this problem. He said that the solar system is stable and he can actually predict exactly where the sun, the planets, the moons, and so on and so forth would be at any given point of time. But then people were intrigued. People looked at the solution carefully. Turned out there was a gap. So he was basically being a bit too ambitious. So the short answer is it is impossible to give a complete answer. One can never, with full certainty, complete rigor, solve this dynamical system and say where planets and moons and the sun will be at a given point of time. But why is it so difficult? Yes? Yeah, so sure. The question is whether the solar system is stable, meaning whether this system where you have the sun and you have the planets revolving around it and the moons revolving around the planets, whether the system is going to keep its stability like it has been for the last several billions of years, or will there be a point in time when things will crash onto each other? Stability will be destroyed. That's the question. The answer is, it is not possible. It is proved that there is no way to give a complete answer to this question. This is an unsolvable equation, so to speak. There are equations in math that you cannot solve. Yes? it's not about being NP-hard. You cannot write down a complete solution of this particular problem. There are differential equations, there are integrals. Most of the integrals that people do work out in their school, these are tailor-made so that you can solve it. Most differential equations, most functions that are integrated are not solvable. You cannot write a closed form expression for these things. So this is one of that kind. You cannot. And then there are other difficulties. In order to even model this, you need to know the exact weight, the exact masses, and the exact gravitational interaction and stuff like that, which is practically impossible to find. However, what Poincare really did, that's the longer answer. Poincare basically considered a utopian situation. Let's think of the sun as the main character, and let's think of this, the planets revolving around it and the moons revolving around the planets, and let's completely disregard the gravitational interactions between various planets. So small things, because mainly the sun is the largest, heaviest object, all other things are smaller. They do influence each other, they do interact with each other gravitationally, but let's ignore that gravitational interaction. Under this kind of a simplifying assumption, you can solve this problem. So then the problem becomes solvable. You can write an exact solution. You can say exactly where all these celestial bodies will be at any given point of time. And you can show that there's never going to be a collision. Everything will be stable forever. So that's the point. If all these small parameters, so this is one of the takeaways of these slides. These are small parameters. These are small numbers. The gravitational interactions between our moon and the Jupiter moon, and so on. These are very small numbers compared to the interaction between the sun and Jupiter, sun and the Earth. And if we ignore these small parameters, then stability is guaranteed. And you would think that, well, that's not a big deal. We often ignore small details in life. Nobody actually does a calculation with pi. It has infinitely many digits. You truncate it somewhere and then you do a calculation. But it turns out reality is not as good as utopia. It's a small deviation of utopia, but only a small deviation because these small details need to be taken into account. But those small details matter. The difference is that I'm not doing a calculation once. I'm looking at my system evolve over 1 billion years of time, and those small things can accumulate. Eventually, small things, small errors can become huge, and they can cause the entire system to destroy, to collapse. That's the whole point. And what are the chances that these small details will actually destroy the solar system in 1 billion years? No one knows, because again, that's the whole point. We don't know exactly what the perturbations are. The utopia is understandable. The reality, even if it is a small perturbation or a small deviation of the ideal world, we do not know exactly what the deviation is. The exact masses and the exact interactions and so on. We do not know exactly what these numbers are. So it's not really possible to calculate, and this is why I mean that when I say that you cannot really give a complete answer, that's the point. You don't know exactly what the perturbations are. Depending on what the perturbations are, and this is kind of funny, depending on what the perturbations are, if the perturbation is 0.1, then it behaves like something. And in the perturbation, if the perturbation is 0.1 and then 20 zeros and there's a 1 after that, then eventually the dynamical behavior, the long-term behavior will be completely different. And unless you know the number up to infinite precision, you cannot solve it. All right, so that's the reality. So the moral is that long-term behavior of a dynamical system, it may depend very sensitively on these finer details, the exact parameters, which is what gave rise to the notion of butterfly effect, which probably many of you have heard of. It basically says that if a butterfly claps its wings somewhere in Brazil, then there may be a tsunami in Texas. I think the original metaphor was if a seagull flaps its wings somewhere, then there might be a tornado. And that's more closer to reality, because when a tornado is formed, really, it's not necessarily formed by big changes in weather. It's formed by very tiny changes in weather, just a little bit of change in wind in certain direction. Eventually, over 2 weeks, causes a huge change in the weather system. So that is chaos for us. This is exactly what chaos means. Small change now, eventually can cause a large change later. Now let's forget about dynamical systems. This was about understanding some very complicated object, the solar system. you may say that, well, for now we are living in this universe, everything looks stable, why care, why bother? Maybe you're interested in something much more mundane, something much more plebeian, like finding the roots of a polynomial. So at this point, I'll talk about a little bit of math, which you may or may not remember. But let's look at two examples. Here's a polynomial, x squared minus 1. We all know how to solve this problem, solve this particular equation. If I want to solve the roots of the equation px equals 0, I'm solving x squared minus 1 equals 0. And everybody knows that this guy has two solutions. One is 1, the other one is negative 1. 1 square is 1, negative 1 square is 1. What about this guy? What if I want to solve this one? So the first problem is that if you take any real number x, positive, negative, 0, whatever, its square is never negative. If you add 1 to it, it's going to be a positive number. X squared is at least 0. Add 1, it's at least a positive number, so it can never be equal to 0, which means x squared plus 1 does not have any root in the real line. The numbers that we are really familiar with are real numbers. But however, even if we are familiar with real numbers, we should keep in mind that real numbers should not be taken for granted. When math started, the only numbers that naturally made sense are integers, positive integers. They're called like natural numbers. You add 0 to it, that also makes sense because nothing is 0. Negative numbers also make sense. Your bank balance can go, you can take a loan and you can have a negative balance. So negative numbers naturally make sense, but usually it's all integers. Fractions are important only when you want to divide something, like 5 apples into 8 people, among 8 people and so on. That's when fractions come. But then you can be happy with fractions. With fractions, you can do magic. You can add 2 fractions, you can multiply 2 fractions, you can divide 2 fractions, and you'll never have to leave the world of fractions. The sum, the product of 2 fractions is a fraction. So why do you need square root of 2? Who needs square root of 2? Why do we need square root of 2 then? We need square root of 2 because even in the ancient world, people wanted to measure things. And if you have a room whose sides are 1 and 1, then what is the, I don't know, something like, let's say, 1 meter, 1 meter. What is the length of this guy? The length of that by Pythagoras is square root of 2. That's how square root of 2 kind of was born. And there was a big debate initially when Pythagoras stated this. Several so-called knowledgeable people said that this is all wrong. Square root, irrational numbers should not exist. Everything should be fraction and so on. But then, square roots exist. And basically all real numbers are obtained roughly this way. Not exactly. There are numbers. So the good thing about square root of 2 is that it has this property. Let me write something about square root of 2. You see, square root of 2 square is 2. How about pi? Does pi satisfy any such thing? Can you write pi square equals some integer, or pi to the n plus pi to the 10 minus pi to the 3 plus pi minus 4 is an integer? No, never. Pi does not satisfy any such standard polynomial equation. So getting to pi is much harder than getting to square root of 2. That's why I'm saying you should not take the real numbers for granted. Real numbers are mysterious. But roughly, you should think of the real numbers as the fractions densely sitting into something. And if you take an interval 0, 1, the fractions are basically everywhere. They are densely sitting on the real numbers, on the entire number line. And the rest of them are what are called irrational numbers. And that's what gives you a line. If you want an actual line, where you want an address for every point on the line so that you can measure things, then you need all real numbers. But why? How do I solve this particular equation? I just saw that there is no real number whose square plus 1 is equal to 0. So I don't have a solution to this particular equation in reals. So that's when somebody realized, I think Argon or someone initially, that the real number system is not enough if you want to solve all polynomial equations. You need at least one more dimension. The real line is like a one-dimensional thing. And if you cannot find solutions to your simple polynomial equations like x squared plus 1 equals 0, what do? You want to augment, you want to enlarge your number system a little bit by what? At least adding one more dimension, and then we'll see if that works or not. But what does it mean to add a dimension? Well, we know we can think of the two-dimensional plane. The two-dimensional plane is fairly easy to imagine. I have the real line here, and it's like two copies, roughly speaking, two copies of R. I have an x-axis and I have a y-axis. X-axis here, y-axis here. Everybody knows how to find a point in the plane using x-axis and y-axis. How would you assign an address to this particular point, for instance? Can someone tell me how to assign an address to a point? This blue point. Suppose I have some base point 0 here. Okay, so I think you kind of said it. Okay, horizontal and vertical. Great. So I'll go horizontal, some distance in the horizontal direction and some distance in the vertical direction. There's another way of assigning an address. And that's this, what are called polar coordinate systems. It's equally important, equally natural. You just take a line, you think of a base point, take a line. Now, any point has a distance from the origin. That's what you call the argument. That's basically how far you are from your base point. And when you connect the base point to this other point by a straight line, you see the angle that it makes with respect to your base x-axis. And these two numbers, the distance from the origin and the angle that you make with respect to the baseline, these two pieces of information, this completely determines the point. That's an address. So that's a perfectly nice way of thinking of the two-dimensional plane. But what's missing in the two-dimensional plane is the notion of multiplication. I can kind of add 2 points on the plane. If I have a point x, y, another point x prime, y prime, I might as well just add the x coordinates and the y coordinates. That makes sense. But how do I multiply two numbers in the plane? It doesn't make sense really, right? Intuitively, because on a real line, we know kind of what multiplication means. 2 times 3. 3 things, each of which is 2, and so on. On the complex numbers plane, well, there is no complex number. I haven't defined what a complex plane is. I just have the real two-dimensional plane. But this is probably the best way of thinking about complex numbers. You start with the real two-dimensional plane. You just want to make sense of multiplication on it. Why do you want to make sense of multiplication? Well, that's because why did I even go to the two-dimensional plane? Because I wanted to solve polynomials. And in polynomial, I have x squared, that is x times x. So if I'm hoping that passing from the one-dimensional line to the two-dimensional plane gives me a way of solving these kind of equations, then at least I should be able to make sense of taking a square of a number on the two-dimensional plane. But how do I know how to multiply a point on the plane with itself? So that's why I need to come up with the notion of multiplication of 2 points in the plane. And it must be compatible with the usual notion of multiplication on the real line, because the two-dimensional plane is like an extension of the real line. I know how to multiply on the real line. I just don't know how to make sense, how to extend it in the other direction. For this usual xy coordinate system is not so good. If you write down, well, if you know some basic math, you can write down a formula of multiplication of 2 points x comma y times x prime y prime. There's some complicated formula which tells you absolutely nothing visually. The meaning is the following. The real multiplication is this. You take 2 points, r theta, which is some point over here, another point s alpha, which is some point over here, which means its distance from the origin is s, and this angle is alpha. So it has 2 components, an angle and the distance. If you want this multiplication to be compatible with multiplication of real numbers, you definitely want the distances to be multiplied. Because imagine your 2 points can be on the real line. You can take r and s both on the real line, in which case the angle is 0 for both of them. And then r0 times s0 should give you the real number on the real line, whose magnitude is r times s. So you got to multiply the 2 distances, two arguments. And what are you going to do at the level of the angles? The point is, this is where this interpretation of the two-dimensional plane in terms of angles and magnitude come into the picture. You're going to add the angles. You're going to think of it as a rotation. That's the point. So if you have a point r theta, which is here, this angle is theta. And if you have another point, S alpha, what you're going to do is you're going to add theta to alpha. So let me give a simple example. If I have a point 2, 0, some real number. 0 means in this coordinate system, the angle is 0, which means you're on the real line. So this is my point 2, 0. Another point 3, I don't know, 90 degrees, pi over 2, let's say. Then the product is going to be, I'm multiplying the arguments, so that's 6. And I'm adding the angles, so that's going to be pi over 2. What that means is my initial point was on the real line. I multiplied the argument, and I rotated by the argument of the other guy. So it's just a rotation. So multiplication of two points, and this is what I'm going to call the complex plane. So complex plane is really not an exotic thing. You have the standard real two-dimensional plane that you understand, and you have defined a multiplication on it. That's it. That's what the complex plane is, where multiplication amounts to multiplication of the argument and rotation. Why is this useful? It's useful because this allows us to find an equation, find a solution to that polynomial x squared plus 1 equals 0. Now, usually in school, you're just taught that here is a number I. I is a solution of x squared plus 1 equals 0. What is that I, and why is it here? Now, in terms of the multiplication that I showed you, I'm claiming that this has to be the solution of x squared equals minus 1. So I'm solving the equation x squared plus 1 equals 0, which is the same as x squared equals negative 1. Now, x is no longer a real number. It's one of these complex numbers I just defined, which has an argument and an angle. I mean, a magnitude and an argument, and this angle. Now, if x is 1 pi over 2, what is the square of it? 1 times 1. You're multiplying the arguments. 1 times 1. That's the absolute value. And what is the angle? Pi over 2 plus pi over 2. Pi over 2 is 90 degrees. You do pi over 2 again. Where do you fall? That's an angle pi. So what is the point on the plane which has distance 1 from the base point origin and makes an angle pi with the x-axis? It's exactly the point negative 1. And that's why this point squares to negative 1. And we just call that point I. That's it. Anyone who tells you that I is some symbol which has no meaning hasn't thought about it this way. This is what it is. Great. Now the magic is that I did all this yoga. I passed to another dimension, multiplied, defined this multiplication on this two-dimensional plane just to find a root of a single polynomial x squared plus 1 equals 0. Now, if you give me a new polynomial, I don't know, x cubed plus 2x plus 3 equals 0, am I going to take another dimension to find the root of these guys? Turns out, you don't have to. This two-dimensional plane, where you have defined a multiplication, it contains all the roots of all polynomials of arbitrary degree. That's a deep mathematics theorem, deep theorem of math, which I'm obviously not going to talk about, but it's something that cannot be easily proved using school-level algebra. It requires some real what's called complex analysis. But it's a fact. Adjoining this particular complex number I, in order to find the root of x squared equals negative 1, actually takes me to this new imaginary world of complex numbers where I can solve every complex polynomial. Every complex polynomial of degree n just means, this power is n, is going to have all n roots in the complex plane. Great, but how do I actually find them? It's good to know that every polynomial has n roots in the complex plane, but since the beginning of time, people were interested in actually solving polynomial equations, and this comes up everywhere, but could be a problem of physics, chemistry, biology, computer science. Polynomials come up, and you have to solve those polynomials to find out where they vanish. How do I find them? You might say, well, I know the quadratic formula, so I can solve the quadratic polynomials. Great. If you have seen a little more math, you'll know that there's something called a Cardano's formula to solve a cubic equation, and maybe a Ferrero's formula or something like that to solve a degree 4 equation. Beyond degree 4, we are absolutely doomed because it's a theorem. It's a theorem that there cannot be a formula to solve a degree 4 polynomial equation. Unlike the quadratic situation where you can write down a closed form formula to find the roots of a quadratic polynomial, in degree 5 and higher, there just does not exist one such thing. So how do I actually find them? Of course, this is an old problem. Newton thought about it. So this is what Newton suggested. And I only want you to look at this picture. You have a polynomial P. Newton didn't quite go to complex numbers, obviously. It was before his time. Complex numbers came after him. So he was only interested in finding the real roots of a polynomial. And somehow, using some kind of mathematics, you can kind of make a guess that I have a polynomial and maybe between 0 and 2, there is a root. I don't know exactly what the root is, but somewhere between 0 and 2, there exists a root. So roughly speaking, the graph of the polynomial, this red thing, it intersects the real line at some point alpha, say between 0 and 10. If I could draw the graph and do some numerical analysis, then of course I can find the root numerically, but I don't have access to that. And that's only a numerical approximation. I need to know exactly where it is. So what Newton suggested is, just draw the graph of the polynomial, the red guy, and pick a guess. You kind of know that there is a root alpha over here, but pick a guess. You don't know the number alpha, but pick a guess x naught near the point alpha. Go to the corresponding point on the graph. So this is my point x naught on the real line. The corresponding point on the graph is x naught comma px naught. This is basically the point. If you don't like this formula, all I'm saying is take a point on the x-axis, go vertically up and see where you intersect the red graph. That is the point. Now, if I have a graph, I have a tangent line. You don't need to know math to understand what a tangent line is. It's just some graph, and it's the best linear object. It's the best line that sort of approximates the graph at that point. That's my blue line. That's the tangent line to the graph at that particular point. See where that blue line intersects the x-axis again. That's my green point over here. There's an exact formula for this, which you can write down if you know basic coordinate geometry. It's not hard. And you need to know what the derivative means. The derivative is nothing but the slope of this tangent line. But the point is that with some luck, and of course I have arranged things so that I have luck, my new point x naught is closer to the root than the original point x naught that I started with. So I started with a guess, did some stuff like draw a tangent line, see where I intersect the x-axis and so on, and I got a little closer to the original root. Now the thing is, what should you do at this point? You haven't, do the same process again. That's dynamics. If you got lucky once, why not try again? So that's your point. This was the point x naught that you started with. Now you have x1 obtained in the previous slide. Do the same thing again. Go vertically up, draw the tangent line, see where it intersects. See, you got closer again. So this x2 again has some particular formula. And if you keep, Newton-Raphson is a slight modification, but roughly yes. And the point is, as you said, if you keep doing this, you iterate this particular, so what is this function? This function is exactly this. It tells you how to go from x naught to x1, and then how to go from x1 to x2, etc., etc. So you want to go from x naught to x1 to x2 to x3, x4, and maybe x billion is essentially very close to alpha. So if you keep iterating this, by iteration, I just mean keep applying again and again and again. If you keep iterating this, this is the function that I'll call the Newton function for the polynomial P. If I keep applying this again and again, I may find a root. But the key thing is, I have to, A, start close to a root. So that's what this with some luck means. My starting point has to be close. And it actually means a little more. For instance, if you have a graph that looks like this, and you're trying to find this particular root, and you start with this point here, you go vertically up, you have this point, the tangent line is this, which never intersects the x-axis. So some luck is required. And basically by luck, I mean sufficiently close to the root. But this is like a cyclic situation. If I know what the root is, I will be sufficiently close to it. I don't know, I'm trying to look for the root. So that's one thing, I have to be a bit lucky. Secondly, I ought to work with complex numbers. I cannot just start with the real line and keep applying this equation again and again, or this function again and again, hoping to find all the roots, because this is not going to work for x squared plus 1. Yes?
How long do you try before you figure out that it's also wrong?
Yeah, so there is a way to find it out. The point is, if you actually are close to a root, there's some borderline bad situation, but generically, near the root, so you're converging, you're starting with x1, x2, x3, x4. You want to see the distance between x2 and x3, and the distance between x3 and x4, and the distance between x3, x4, and x5. You want to see whether these distances are shrinking exponentially. If they are not, then they're in the wrong zone. You're looking for something else. You're not getting closer to the root. So this exponential convergence is what you need to find. Yeah. All right. So as I said, Newton iteration, which is like a dynamical process, kind of helps you find a root, but there are two issues. One, we have to work with the complex numbers. That's not an issue. We have already set up complex numbers, but this luck thing is a big problem now. So that's why I want to understand dynamics of these kind of Newton things better. I need to understand what happens when I keep iterating this function on the complex plane in order to solve a simple problem of algebra, how to solve polynomial equations. All right, some history. This guy, Arthur Cayley, he was interested in this particular problem. What happens when you keep applying this Newton function to a complex number again and again and again? And he wrote this. This is from a paper you can Google. I forget the exact name, but if you find Arthur Cayley, he has a paper in the American Journal of Math, 1879, where he said that the solution is very easy and elegant in the case of a quadratic equation. But that's not a deep achievement, because for a quadratic equation, we know already how to solve how to find the roots of a quadratic equation. We can factorize it. But the next succeeding case of a cubic equation appears to present considerable difficulty. And this is what he kind of found. If you look at the dynamics, you look at the polynomial x squared plus 1, look at the Newton function, x minus px over its derivative. You keep iterating it on the complex plane, on the whole complex plane. What he found was that here's the real line. This black thing is the real line. No matter what point you start with in the upper half plane above the real line, start here, for instance, keep applying this function n, you'll keep getting closer, 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 closer to this particular root I, which is one of the roots of x squared plus 1. If you start just by symmetry, if you start below the real line, no matter where you start, keep applying n, eventually you'll get closer to negative y, which is the other root of the equation. So a perfectly elegant, easy solution. So the only thing you need to avoid is the real line. If you start on the real line, of course, you're not going to go to any root. You see a little bit of chaos in this, though. And the chaos is that a computer, for instance, never knows what's a real number. Unless you have to, it only knows that depending on how you feed a number to a complex number, to a computer, you have to tell that the imaginary part is 0. And telling a computer that something is 0 is very difficult. So if the computer thinks that your real number or the number you gave is not exactly real, but slightly above the real line, it's a small mistake it's making. And maybe you're very generous and you say, yeah, fine, make a small mistake, I don't care. Let it run the program 1,000 times. Instead of staying on the real line, it'll take you there. And if it makes a mistake in the other direction, it'll take you there. So a small change here, after 1,000 iterations or so, can take you to very different end results. Anyway, this was the good part of the story anyway. Now the question is, what should the cubic situation look like? Of course, Cayley couldn't quite figure out, but then that was 1879. We know so much more math, so maybe we should know. Maybe this Cayley's situation was you have one line, everything above goes to something, everything below goes to something else. Maybe here I have, instead of having two regions, I have 3 regions like this. And everything here converges to red. Red, blue, and green are the 3 roots of a cubic polynomial. Maybe everything in this region goes here, everything here goes to the green, everything here goes to the blue. Or maybe I have some regions like this, red, blue, and green, and everything in these regions converges to these roots, and there's some black region which has absolutely nothing to do with the root solving process. If you start with the black region, you just veer off and you go somewhere else. Or it could be something else, right? It could be like, I don't know, it could be like 3 regions like this, where you have red here, maybe blue here, and green there. I don't know. It's another guess. Maybe that's my scenario C. Any idea? Anyone wants to take a guess what's likely? This is an unfair question. It's an unfair question, so I should not ask. The point is, Cayley had no chance. Cayley had no chance because he didn't have access to a computer. And unless you have seen what's really happening in the cubic situation, you have no chance either. This is not something you can imagine by pure thought experiment. And this is, yes. One slide, yes. It is the real line. Yeah. No, that's a scenario. I don't know. This is just a conceivable scenario. Some separation line. It could be a nice, I don't know, parabola or something. That's what I'm suggesting, that maybe it looks like this. You have some region where all points converge to this root under Newton. Here, all points converge to this, and here, all points converge to that. And they are separated by some lines. That could be, I don't know, some nice parabola. It could be a much more wiggly, fractalish line. I don't know what it is, but that's my question. Yes.
But what is the polynomial? You just said cubic situation.
What's your favorite polynomial? X cubed minus 1? X cubed minus 1. It has 3 roots. You have to go to the complex plane. One is 1. The other ones are the 2, well, roots of unity. There's 1 omega and omega square. This, I haven't told you what is true. I'm asking a question here. I'm asking, what should the cubic situation look like? Oh, I see. So it's my fault. I'm sorry. This is a question mark. Is it scenario A? Is it scenario B? Or is it something much more complicated? That's my question at the moment. Yeah. And I'm telling you that it's none of these. It's this. So if you start with the polynomial x cubed minus 1, a little bit of complex, well, maybe in 11th standard, 10th standard math tells you that it has 3 roots in complex plane. One is at the point 1, because 1 cube is equal to 1. But then there are 2 other complex roots, which are called omega and omega squared. It's not hard to find out those roots using what I told you earlier. But let me not. Yeah, why are they here? So I can actually tell you why the 3 roots are here. This is the point 1. This is obviously a root of this. 1 cube is equal to 1. What is this point? This point, this is my origin. the way I'm thinking of complex numbers, I'm looking at the distance from the origin, and I'm looking at the angle it makes with the x-axis. This guy, it has distance 1, and it makes an angle 120 degrees. If you raise it to the third power, the distance 1 is getting raised to the third power. It's staying as 1. The angle was 120 degrees. You add it with itself 3 times, you get 360 degrees. So you come back here. This guy, it also has distance 1 from the origin, and it makes an angle 240 degrees with the x-axis. If you raise it to the third power, my notion of multiplication was the distance is getting cubed, so that's 1 cube. The angle is getting added to itself 3 times. So 240 plus 240 plus 240 is 720. 720 is 2 full turns, and you're back here, which is why these are the 2 roots on the complex plane. And what the picture is suggesting is that there indeed are 3 regions, but regions in a much more complicated sense. Think of everything that's red to be some region, some set. The reason why I don't want to call it a region is that it's not really connected. Like there's some piece over here, there's some piece over here, there's some piece over here, and there are infinitely many pieces here. But some kind of generalized region or set. Like not all countries are connected. There are islands, right? So it's fine. So there's a red part, there's a blue part, and there's a green part. And if you start with any point in the red guy, apply the Newton method corresponding to this, you will converge to this root. And the same is true for the other colors. All points of common color converge to the same root. And depending on your starting point, if your starting point is, say, somewhere here, if you start somewhere near the root, you're safe. Of course, you'll go there. But if you start far away, say over here, if I zoomed in here, there's an interesting self-similarity of this picture. The picture over here looks exactly like the picture there. At all scales, if you keep zooming in, you'll see this picture. So which means that the important feature of this point is that red, blue, and green, all of them exist in a small neighborhood of that point. So if you zoom in there, what does zooming in mean? Zooming in means that I'm sort of looking at points whose first 1,000 decimal digits are the same, and things only differ after the first 1,000 decimal digits or something. But by making small changes in the tail of the decimal expansion, my point can either be blue or red or green. So I have no control over, unless I know all the digits of my point, which a computer can never remember, I have no way of finding out whether my point is in a red region or a blue region or a green region, somewhere over here. And this small chance, this small error, this small uncertainty, it gets amplified when you keep iterating the function. Eventually, it will take you here or there or there. Yes. Sorry. Yes, exactly.
You find the green path in the contours to end up in the red. You have to keep yourself in the green path.
Yeah, but the thing is, my iteration is not a continuous motion. The point is not moving. You're jumping between back here and there. So this is, okay, maybe this is something I should have said. There are 2 different kinds of dynamical systems. One is you put a red drop in a river and see how it flows. That's a continuous trajectory. I am applying my function to a point. It goes from here to there, to there, to there. It's not doing. That's the difference. It's a discretization. It is. It is. Eventually, all green points will eventually land in a small neighborhood of this. It's jumping from one component to another. It's always going to be in the green part. It'll go from one green island to another, to another, to another, eventually going to this big green island. Yes.
When it's jumping from the green islands, say I'm at a very far island, is it 100% probable that when I'm jumping, I'll jump to an island closer to the point?
Yeah. Yeah. That's a deeper question, but roughly the sizes of these islands. Oh, sure. Yeah. So the question is whether it's guaranteed that I'm never going to jump from a green island of very tiny size to a green island of a large size to a neighboring.
There is a point. There is a green point.
Okay.
The point is the green. This is the actual root.
and say I select a point in a green region which is very far away from that root.
Mm-hmm.
Now, when I'm jumping from the islands,
Mm-hmm.
is it such that when I'm jumping, the point I selected was at a distance s.
Mm-hmm.
If I'm jumping, would the distance be less than s or will it be more than s?
All right. So the question is whether the distance from a root is decreasing along the way. I start with some point. I have my green root somewhere, and I start with a point which has distance 1000 from the root, and I apply my method. Is the distance going to decrease? Not necessarily. Initially, anything can happen. This is a bit like eventually you can guarantee that things will converge to the green, but eventuality is like a long-term gain. It's like a share market thing. First 2 years, anything can happen. Eventually, things will converge. All right, great. So, so the person who drew these kind of pictures, so this is John Hubbard, who was teaching in Cornell around that time, 1978, 1979, when he was teaching a numerical analysis class on a numerical analysis course, and Newton method came up over there. And some student asked him, what happens if I choose a point in the complex plane? And can you iterate? And John Hubbard was kind of interested in certain dynamical systems. And that's when he realized that we know so little about the iteration of a simple rational function. Because, so what is a rational function? You see, my polynomial was, say, x cubed minus 1. And my Newton is x minus px over p prime. And my p was x cubed minus 1. At this point, I'm going to assume that you know how to differentiate. If you don't, it doesn't matter. It's just a formula. So this is my Newton. (3x²). And this means I have, what do I have? 3x cubed minus x cubed plus 1. So that's 2x cubed plus 1 over 3x². This is what the Newton function looks like. X minus px over p prime. For the polynomial x cubed minus 1, this is the exact form. These are called rational functions because these are like, so you should think of rational functions to polynomials are what rational numbers are to integers. The ratio of two integers is a fraction. The ratio of two polynomials, you think of polynomials as integers, and the ratio of two polynomials is a rational function. So Hubbard realized that we know so little about the dynamics of rational function, we need to have a systematic study of these things. And he also understood that everything depends very sensitively on the starting point. And of course, everything depends very sensitively on the coefficient of the polynomial itself. This picture is only for the polynomial z cubed minus 1. If I chose a different polynomial, the plane will look very different. The coloring of points converging to various roots will look very different. I should say one more thing. This picture is slightly deceiving. It gives you a feeling that essentially all points in the plane converge to either of these three roots, except maybe the boundary points. Like there are borders, the boundaries, think of them as, I don't know, countries and islands, and then you have the border. The borders are obviously neither here, not there, not there. So if you start with a bordering point, you'll stay on the border, you'll never go to a root. But that's a very small thing. Like nobody really cares about the border between two countries because the border is like a one-dimensional thing. It's not really a region. So this picture makes you think that maybe for every polynomial, other than these small bordering regions, all points will eventually converge to a root. That is not true. For certain polynomials, I can write down the Newton map for which they're going to be some black region. And if you start on those black regions, you are never going to converge to any of the roots. So there'll be like a black island here and a black island there. And there'll be like you go from this black island to that black island, and you come back to this black island. And you keep going back and forth between them. So you never go to any of the roots. Such things can also happen. So this is what Hubbard kind of understood, that we need to understand dynamics. We need to study the dynamics of these rational functions on the complex plane. And that's the dynamics of complex numbers, dynamics of functions on the complex numbers. And of course, the point is that these experiments can only guide us, but they don't really tell us why things are happening. Why? I mean, this is a why question, right? A mathematician doesn't necessarily doesn't just want an answer. An answer is only satisfactory when you understand why it's true. So that's what we want to understand, a systematic understanding of why exactly all these things are happening, why the picture looks like what it does. And this is where the Mandelbrot set lives. I don't know, I'll probably not have much time to talk about the Mandelbrot set, but I want to talk about something much simpler. Instead of, I do want to develop a general theory of dynamical systems of these on the complex plane. I want to understand how small changes can eventually give rise to big changes and so on. But then to develop a theory, I have to start with something very simple. Now, what can be more simple than the function z squared? So you start with the function z squared, which you want to iterate on the plane. What happens when you iterate the function z squared on the plane? Well, this is the unit circle, meaning this is the set of all points on the complex plane that have distance 1 from the origin. So remember what happens when you multiply two complex numbers? The argument, the distance from the origin gets squared, and then there is a rotation bit. But if you take a point outside the unit disk, its distance from the origin is larger than 1. When you square it, it gets even bigger. Any number that's larger than 1, upon squaring, gets bigger. Then you square it again, the number gets bigger and bigger and bigger, flies off to infinity. Everything outside this unit circle, if you keep squaring it, it flies off to infinity. Everything inside, here the distance from the origin is less than 1. Now, if you start with any number that's smaller than 1, and you keep squaring it, it goes to 0. It gets smaller and smaller, and it goes to 0. So every point here converges to 0. Every point outside converges to infinity. This is very similar to what Cayley observed. Instead of having an inner disk and an outer disk, here he had an upper half and a lower half, but these are roughly the same objects up to a change of lengths. Here you have two regions. On one of them, everything converges to this, and on the other, everything converges to that. And z squared shows you exactly the same dynamics. But then, what is the interesting question to ask? There's nothing interesting going on here or outside. Something is happening on the unit circle. If you're on the unit circle, the distance from the origin is 1. You're squaring it, the distance remains 1. So you stay on the unit circle. So what is exactly happening on the unit circle? What is happening on the unit circle is, well, if you take a point on the unit circle, it makes some angle theta with the x-axis. Squaring means nothing happens to the distance part. The distance is just getting squared. But something happens to the angle. It's theta plus theta. You're again rotating by theta. So initially, the point had an argument theta with the x-axis. Now it's going to be 2 theta. So the angle is getting doubled. That's all. And that's the doubling map. You take a point. So yeah, roughly speaking, that's the doubling map. Think of the entire angle instead of 0 to 2 pi, just think of it as 0 to 1. Doesn't matter. And then the angle is getting doubled. And the mod 1 here is to say, this mod 1 is a very interesting thing. There could be a different talk about what mod 1 means. The mod 1 and the international date line. If you think about it, you have the international date line. And what happens? Why does the time change by 24 hours across the international date line? Because it's a circle. The Earth is circular. There's no way the time can increase and keep increasing and keep increasing. At some point, it has to come back to the same time. And then when it comes back to the same time, there has to be a change. There has to be a jump discontinuity. Because the time was increasing from hour 0 to hour 24. It cannot be hour 25. It has to cut down to 24. That is what mod 1 means over here. When you add two angles, say you have a point here at angles, say 240 degrees or something. When you add 240 plus 240, you get 480. 480 doesn't make sense. There are only 360 angles. So 420 means 360 plus 120. So you forget the first 360, and the rest is 120. And that's what I mean by mod 1 over here. I just want to say that this doubling is an extremely chaotic game. It looks like a very simple operation. You have the line 0, 1, and you're multiplying and subtracting 1. That's all you're doing. But if you keep doing this, something very strange happens. All the fractions on the real line, which are like everywhere on the real line, they have a finite life. At some point, they come back to themselves. They have a short life, so to speak. Whereas all the other numbers, anything that is not irrational, they keep jumping back and forth. Some of them densely fill up the entire 0, 1. So it's possible that you start with a point in 0, 1 and you keep doubling it, modulo 1, and it's going to fill up the entire interval 0, 1. You would then think that, oh, if such complicated numbers exist, maybe pi is one of them. No one knows. This question is still open. And just maybe one last slide. If you want to understand, so you understood what z squared does. If you want to understand what happens for a general quadratic map, z squared plus c, you have to understand this gadget. This is called the Mandelbrot set. This picture contains the entire information of the dynamics of all quadratic polynomials. It contains the entire picture in it, the entire sort of all the information, and how the dynamics changes when you go from one polynomial z squared plus c to a nearby polynomial z squared plus c prime and so on, whether the small change in the parameter causes a huge change in the qualitative dynamics or only a little bit of change in the qualitative dynamics. All these things are hidden over here. And maybe I'll just end with how complicated the Mandelbrot set is. There are copies of the Mandelbrot set in itself. You can go in deep scales and see many copies of it. There are some regions where the Mandelbrot set looks hairy and it has a full measure over there and so on and so forth. And there's a huge theory of math dedicated to understanding this model because this is one of the simplest yet fully understandable models of chaos. Thank you.
While we wait for the online audience, if anybody has a quick question, do it. Otherwise, we'll break for chai, of course. Let me just check.
How is the Mandelbrot done by computer or not?
Yes. Yes. All pictures. So, I think this one may be 2000 iterations or something. You don't need too much because it's quadratic. And so in order to see repetition, when you zoom in, you need more iterations. Because when you do 2000 iterations, it will only give you a good picture on the top scale. When you want to zoom in and see, zooming in, as I said, really means understanding precise dynamical behavior of points up to 100 decimal digits, for which you need more iterations.
This Mandelbrot set is basically, from what I see here, is many such different shapes, say, iterating again and again throughout a given area. So is there any pattern that is observed by which we can predict the set further without calculating also?
Guys, let's do one thing. I think we should end the online stream, go for chai, and then come back. Okay, because there'll be a lot of questions. Let's just take a break for chai because the chai will get cold. It's been waiting outside.
Sure.
Yes.
Thank you.
So just for the online audience, just announcing again, 2 weeks from now, we have a thing on ultra fast and ultra short lasers, ultra high power and ultra short lasers, Sitare Zameen Par at Ruparel College. A month from now, astrophysics happening at Prithvi Theatre.
Thank you.
Okay, great. So leave everything here.